Hello, everyone, and thank you very much for coming. My name is Sabil, and I'm the co-founder and CTO at Soundrop. So I'm here today basically to tell you about how we used Erlang to build a real-time music service. But before I do that, I would like to tell you the story about how all of this happened. My personal first contact with Erlang was in 2004, I believe. I was still a student in engineering school, and this friend of mine came and was like, Ali, you really totally should check this language. He borrowed the book from the school library, and he's like, yeah, you need to check this language. It's really totally awesome. So I borrowed the book and started reading. I think I read the first chapter, the second one, and maybe the third one. Then I just yeah, I gave up. So I returned the book, and next time I met him, I told him, like, this Erlang stuff looks neat, but seriously, I don't see what I can do with it that I can't do in PHP. So that really was it. That was it for me with Erlang. Later, I got involved with IM protocols, and especially reverse engineering of the MSN protocol, including the webcam and all these features like nudging windows and whatnot. And which led me to start working for a video conferencing company that later got acquired by Cisco. While working there, I worked on building what they call like a unified communication solution that was based on XMPP. So it was more like a research project, and at some point we had to pick an XMPP server, given that it was a unified communication solution built on XMPP, right? So we looked around. There was like there was OpenFire, Tgaze, and eJabberD. I didn't know much about Erlang, so my experience with it was pretty limited. So we ended up picking Tgaze. We worked with it a bit, started like modifying it, integrating with our system. Then it got a bit complicated because I think, at least back then, Tgaze was like a Java server written in C style, basically. And so at some point, I just like went on holidays, backpacking somewhere in Southeast Asia. And then when I came back, the guy with whom I was working, who happened to be my friend from the university, replaced the XMPP server with eJabberD. So now I really had to learn Erlang. That project continued, and I moved to another project that was about building a cloud kind of, because back then cloud was hip, and we needed to build a cloud directory. And that was my second encounter with Erlang, where we were looking at React back then as a storage backend for this. I left Cisco at the end of 2010, and then I started working on, a few months down the road, Soundrop was born. So let's talk a bit about Soundrop. I don't know how many of you have used it, but it's essentially a social music discovery service that helps people sharing music and discovering it in real time. So it works in such a way that when you go into Soundrop, you are presented with a set of live rooms that you are able to enter, and then you start listening to music in sync with other people. Sounds like radio so far, except that you are able to also add tracks to these rooms, and people can vote for the tracks, and tracks with most votes get played first. They can also chat with each other. You can see where people are connected from. And it also happens to be a multi-device, multi-target experience, where today we have an application within Spotify, but you also have a web version of it and an iOS version of it, and also something inside Facebook. So maybe I should show you all of this. So how does it work? Yeah, it's here. OK, so this is basically like, if you go inside the app finder here in Spotify, it's not, you can go, Soundrop today is the 4th app for some reason. Hopefully it will load, yep. So here you see like a set of rooms that we have. There's like tens of thousands of these rooms, actually. And there's like rooms for genres, rooms for different artists. And for example, if you look at the chill out room here, there's like 762 people listening or 763 people listening right there, right now. So I'm able to enter that room and the music is playing, basically. So there's like, these people are here. It's possible, this is basically the playlist. It's possible to vote for tracks. Like, for example, if I vote for this one, it's going to move up. It's possible to chat with other people. And it's essentially like a community thing. Oops, I'm tired of this music. So we also happen to have the same thing on the play.soundrop.fm. We have the same thing on the web as well. Same story, 763 people there. Except that this time, we actually use YouTube for the playback. So we match the whole thing. And if when you're inside Spotify or on the web, you actually are able to listen to the same thing. We are trying to basically build as many music providers as possible, and we're still working on this. There's an iOS app in the work. There's also a Facebook app where we got like, I guess there's quite a few Swedish people here. We got ABBA basically to put Soundrop in their Facebook page. Yeah, time to get back to the presentation, I guess. Where is it? There we go. So this is essentially a very simplified overview of how Soundrop is built. So we have like all these clients at the top. We have like some web clients and some native clients. Our web client, I mean, even the one running inside Spotify is actually entirely built in JavaScript. It's a very heavy JavaScript application. Before starting this, I didn't really know JavaScript. It's a good language after all, I think. Then we have something that we call Wocket. Because back then when we started working on this, there was Socket.io, which I think is not really great. There was no sock.js back then, so we ended up building our own kind of transport system where actually we're able to send messages back and forth for the web. So it supports like things like WebSockets. And that's actually where we probably learned a lot, in the sense that there's all sorts of like nasty things in a network. That you would establish like a WebSocket connection, but then the messages would only flow in one direction. So we have this server there that actually implements its own kind of protocol just to make sure that the network works. Then we have sessions. That's basically where the green part is the Erlang part. We have sessions that represent people connecting, especially if they use like a transport that's not always connected, then there's like a store and forward kind of logic there. And we also have like user processes that represent a unique user. So for example, a user can be connected from multiple devices, and we'd like to make sure that all these sessions are in sync. So we have a feature there, called Recent Rooms, that allows you to, if you visit a room on your mobile phone, it immediately pops on all your devices and everything is in sync. If you receive a notification here, everything is really synchronized. And we do that through an Erlang process per user. And then we have what we call spaces, which is our technical name for rooms. And inside this space is like an Erlang process today as well. And inside these spaces, we have other sub-processes that manage the application, the chat, and the membership. So from a supervision tree, this is a really simplified version because there is a lot of like third-party integration services in our tree, like integrating with Spotify, integrating with Facebook and Twitter, all these things that are there that I didn't put in this slide. This is just like the core of it. We also make use, I don't know how many of you attended the previous talk, but we make use of quite a few special processes in the case of session. The session process is not a gen server. It's not a plain spawned process. It's really like an OTP. It fits into the OTP tree, but it's a custom gen server that actually, or a custom state machine that actually switches between whether it's supposed to store the messages or to forward them to the connected socket. And the same is true for the space, which is sort of a supervisor to these three applications that are running inside. One of the challenges that we have seen and that we will continue to see is that something like this is really, really difficult to scale. Why? Because we have like a shared state where there's people connected from all over the world. We're trying to synchronize the playback, but we're also allowing every single person connected to modify the state. They can vote, they can add tracks at any point in time, and we need to make sure that everything really makes sense there. So eventual consistency is just something that we can use. We need something really much stronger than that. So now that I've presented a bit, like just a brief overview of Soundrop, maybe I can talk a bit about Erlang. I assume everybody here is a bit like is familiar with Erlang, so I don't really need to present that. But how did we end up really there? I mean, my experience personally and the experience of everybody involved in Soundrop was pretty limited when we started on Soundrop. But we have this culture where we like to explore things. We like to try to find what's the best tool for the job. So while developing Soundrop, we did a lot of product exploration. So the story is we were not always this. We were something else before. And while doing that, we're also like exploring the technology side of things. Yeah. So this has been our journey to Soundrop. Soundrop started as a project where we wanted a product where we'd be putting jukeboxes back into venues. So we wanted to put jukeboxes into different venues and allow you to control them through your mobile phone. So we built this thing. We built the initial prototypes in Python. So there was it worked. We even actually managed to deploy it in a venue in Oslo where we're based. And people were able to add tracks and vote and all these things. But there was a challenge in the sense that given the product we were trying to build, it was sort of enough to have a server that was just relaying messages. So we have like a master player running in the venue, and then all the clients, they just need to connect to that somehow and get the state. What is queued right now? What's playing right now? What can I add? So building an Erlang, a Python server was, I mean, it worked. So, but it was based on polling. So what happened is that the mobile phone will connect to the server, and then we'll ask what's the status of that specific place or that specific venue. So it will receive that, and it will just like poll every, I don't remember, but every 30 seconds to see what's the new state, what's happening. I mean, it's far less than ideal. We'd like to have something much more alive. And also, I mean, it worked for what we were trying to do, but we tried to improve it. So I remember node.js was starting to be really hip back then. So I was like, okay, this sounds like the technology that maybe we'll be able to use. Especially, I mean, we're going to be building the front end anyway in some sort of JavaScript because we're using like mobile web. So it makes sense to use like JavaScript in both ends and see if it's going to work. That was Node 0.3 back then. I have no idea what's the state of things these days. We tried. We built a prototype. I just have to say I ran away, literally, because I couldn't believe that actually something like Node.js would be like solid enough for building any kind of servers. I had some, of course it was a prototype, but it was really disturbing to see that if this client sent the wrong kind of message, it might code an exception in the server, which will just bring the whole server down. I was not really happy with that. I wanted something much more solid. So started with like back to the roots. We went back to Python, built something using, I don't know how many of you are familiar with Python, but used like G-event and Redis to basically like work as a pub sub system. It worked pretty well, except that one day there was a mistake, and we started leaking memory. How did that happen? We had like a list somewhere, and then we're just modifying it, appending things, thinking that it's going to return a new list. But it did not. It just like updated the list. So we end up like accumulating more and more. It was really, really hard to track what was happening. So we decided, there was like Easter holidays, and we decided to give Erlang a try, and to try how that would work for what we were trying to do. So we still had this jukebox idea, so we just built the same thing again in Erlang. It worked, I would say it worked pretty well. I struggled a bit in the beginning, but it worked really well. It had like all the characteristics that we needed, and even more, because it's actually the fact that we chose Erlang back then, when we were building a jukebox, that actually allowed us to build Soundrop that we have today. So, why Erlang? What makes Erlang so much better for us compared to the others? The first thing is concurrency. So over time, we started with this jukebox thing, where the master was the venue. We had like a software around the venue, and that was dictating everything. Into moving that logic into the server, so the server became the master, which means that the clients could get disconnected, or they will be the server itself is the master. And we need concurrency, simply because we manage a lot of rooms at the same time, and we manage a lot of sessions. So Soundrop is still a pretty small service, but at peak time on one single server, we had more than 22,000 concurrent people connected on that. It doesn't sound like huge, but when you think about like what's happening behind and all the coordination is happening, it's actually quite massive. And at any point in time of the day, we have more than 1,000 active rooms that actually are playing music, synchronizing the playback, and doing all that work. We also had this event where there's this new and upcoming artist called Kendrick Lamar. I don't know how many of you know about him, but he has some pretty dedicated fan base. And he happened to tweet, "I am on Soundrop." So what happened is that the following 15 minutes, we had something like 2,500 people just pouring in. We also had another event that was much bigger. This one was a bit more advertised, where we had something like more than 6,000 people in one single room. And we managed to synchronize the playback of all these 6,000 people connected from across the globe. That brings me basically to the next point that we really, why does Erlang work for us? It's fault tolerance. The thing is that we have these rooms and we have these sessions, and we control the playback for different computers that are connected. Essentially, in Soundrop, as we know it today, the server can send at any point in time, play this track at this position, or with this number of milliseconds from the start. And all the clients will actually will do that immediately, and they will try to compensate for all the buffering, and they will really start playing in sync. Of course, there's like always the network latency, but we always try to compensate for that. And it's really annoying if it should be really. I personally hate it if my music just gets interrupted. That's probably why I'm paying for Spotify. I just don't like to have my music interrupted. I assume it's the same for most of us, really. So it should be really disastrous if we trigger a bug somewhere in our room logic where we're synchronizing this playback that would cause all the playback across Soundrop to just stop. That's not ideal. That's far from ideal for us. So we had actually events where, especially after rolling new releases and new version of the server, where some very specific scenarios triggered a crash in the room. And only that room just went down and just restarted, and people rejoined that room and just continued. Whereas the other rooms in Soundrop just stayed unaffected, and it just worked. We also sometimes have had some people having fun with our servers. We tracked them down. They were like some students in some high school trying to flood our servers with messages. And what happened essentially, they just get disconnected because their session just detects it's being flooded, and then we just kill the session, and that's it. It just continues. And the worst kind of thing is sometimes, we rely on external services. We rely on Facebook, we rely on Twitter, and on Spotify. And sometimes their services are down or are not really working properly. because we didn't, I mean, when when you are developing a product in a startup, we are just trying to make it to ship as fast as possible. So sometimes we didn't really check properly. Sometimes we didn't validate things. And what happened in those cases is essentially the room that triggered that scenario would just crash and get restarted, and everything else would just continue. All the other services would just, all the other rooms would just be there. We don't really do hot code upgrades, like as in OTP-style hot code upgrades yet. I wish we would be able to do that. That's actually would be really awesome for us. But we don't really need it because we can restart the server within 5 minutes. We just look at the downtime when we have the least amount of users, and we deploy them. But sometimes we need to patch a module to fix critical bugs. We are continuously improving the software, and that's just totally important for us, because if we had to restart the server every single time we fix a critical bug, it would be disastrous, because everybody will get disconnected, everybody's playback will get interrupted. There was also this funny, or I think it's funny, for me at least, story where we had an event scheduled. We actually helped what's his name already? Alesso from Swedish House Mafia to organize an event in Soundrop. It was Universal Music, if I recall correctly. And 15 minutes before the event, there was one of these third-party services that we relied on that actually changed their API. They actually deployed a new version that didn't have the API that we were using. So you can imagine the level of stress when we're trying things and you're just like, uh-oh, in 15 minutes it starts, we have to fix this, we have to change it. We didn't want to restart the server because there had been a lot of marketing effort into bringing people into that room, and you just don't want them to just get disconnected, right? So what we did was actually to quickly implement a new version of the module and SSH into the machine. And it was like a multi-node back then. So I think we had 2 machines. We just loaded an NL, and then it just got updated in all the nodes. And that was pretty awesome for us. The other story, it dates back to, I think it was 3 months after we launched the initial product within Spotify. There was this funny guys, I think they were 7 friends or so, and they just decided that Hakuna Matata was a really awesome song. So they went to all the rooms and started adding Hakuna Matata and then just voting it. And because they thought it was a relaxed song and they really loved it. So, I mean, we didn't have any mechanism back then for fighting trolls or for blocking these people. So we tried to figure out a way to deal with it. What we did essentially was to hard code their user IDs into a module and just hot patch the module so that they are not able to add any track. That basically was the. So this hot code patching is pretty useful. It's more than just for upgrading. Sometimes you can stop trolls in our case. The last one, or not the last one actually, I have another one after that one, is the fact that Erlang is soft real time. What does that mean for us? We're trying to synchronize playback across the globe. We're trying to never be late. We're trying to have a very predictable timers. So if we're running inside a system where garbage collection or something can cause delays, random delays, where sometimes you're 200 milliseconds here, 500 milliseconds here, because something has happened elsewhere, it wouldn't really be a good playback experience. People will be skipping things because the reason why we do synchronize the playback is to avoid clipping tracks at the beginning and at the end. So it's actually, you avoid this clipping, where we just cut to resync to the next track. We really don't want that to happen. So we have a lot of timers, especially inside the playlist application, as I explained earlier. So the playlist has timers to know when to move to the next track. And the fact that we're soft real time is what allows us to do that. If we continue using node.js or Python, I don't think we'll be able to have 6,000 people, large rooms that actually are not going to affect the playback of the 20 people rooms, because those things are totally isolated, and the whole thing is soft real time. So we we can at least expect the system to run in a predictable way. And well, to be honest, I think we just love it nowadays. You know, our background is most like C programming, Python, a bit of Java. But then when you start discovering Erlang and OTP, you just it feels like something new, something refreshing, something that it's what you have been looking for, but didn't really hear about it before. So, as I said, we just really love Erlang, and we find it amazing. So, but the next slides are going to be a bit negative. So I'm going to talk about our mistakes that made it much more difficult for us. So when you read about Erlang on the internet, it says you just makes your stuff scale. That's not really true. I mean, it helps you build scalable stuff. It doesn't really it doesn't automatically make your stuff scale. And that was really hard for us to understand, because we didn't really know the language or the runtime that well. And in the case of Soundrop, as I said earlier, because of our system, it's pretty difficult to scale. And that's something I'm sort of missing or wishing that Erlang had, which is some sort of framework or foundation for building distributed systems. I know React Core supports a subset of the distribution systems problems, but that doesn't work for us. We need something that's consistent. So the second thing that actually was a bit surprising for us is the fact that the VM can crash. We assumed that if we run out of memory, the process that tried to allocate that memory will get killed. Wishful thinking. That really wasn't the case for us, especially in the early prototypes or the early products that we deployed. We had the VM crashing sometimes when we were running on a 32-bit system. Also, Erlang, I think or OTP, Erlang OTP, the distribution we have today, doesn't really fit that well into a Unix/Linux environment. When you try to use things like run Erl and to-Erl, you get bitten by some quirks. It doesn't handle signals out of the box like SIG-HUP and SIG-term. And it doesn't really do creation of the PID files, essentially things that you'd expect from a server. Those are difficult to do today in Erlang, or in Erlang OTP. That one is basically related to the Erlang, the run Erl and to-Erl. Somehow, back in last year, I think, we're still using run Erl and to-Erl. And when you combine these with SSH, the shell hangs. I just recently saw some mails in the mailing list about it, but back then we really didn't know what was happening. So it just the shell just hangs, stops responding. It happens if you disconnect from one of them and you have an unfinished expression in the previous shell. We also had issues with I/O being blocked when using send file on R15 in the early R15s, and we still see sometimes HTTP/C hang forever because it's waiting for something to receive that just never happens. Yeah, this one links back a bit to the Erlang doesn't automatically scale for you story. So we wanted to have support for this clustering, and we just didn't want to think. We assumed that maybe it would just do multicast for us, or it would do something magical to make sure that the network is not congested. So we just put we used gproc in a distribution with GenLeader. And what happened is that we had a lot of inter-node traffic, because clients will end up connecting on this node, for example, 100 clients connected on node 1, where the room is running on node 2. So all the messages sent from the node 2 to these 100 clients will have to be sent 100 times across the network. So we end up congesting the network and causing basically the heartbeat timeout, which caused net splits or split brains and gproc was not recovering from these, and we had no idea what was happening. I mean, we're total noobs in that area. the last, I mean, this is like a summary of all things. I'm just trying to remember all the issues we had or issues we saw. But some third-party libraries were pretty much unreliable. Historically, we decided to use MongoDB. I'm very sorry about that. But because we're venue-based, the original code for the jukebox needed to do geolocation search nearby, all these things. Which database did that easily back then? That was just easy to get started with. Well, MongoDB did that, so we picked MongoDB, and we have been running with it since then. And we only use the database really for persisting the metadata about a room, and also for flushing the state of every room every now and then to be able to restart the server and continue from a known state. So the MongoDB is not really great, but the MongoDB driver was worse. So it was not really working. So and it was causing like all sorts of weird behaviors, because apparently the person who wrote it came from Haskell, and it was designed so that you have these monadic variables that are implemented using gen servers and whatnot. The other issue that we had is we wanted to integrate with like Twitter, we wanted to integrate with Spotify, so we had to roll these things on our own, basically. Especially the Spotify one, where we had to use libSpotify in C, and then integrate all of that with Soundrop. I was also surprised to see that there is a lack of web-based monitoring tool. Correct me if I'm wrong, but I cannot really find something that I'm really happy with. I'm still like, for example, Observer has been rewritten recently, but I really wonder why is it written in WX for something that's meant to be run for servers. Why is it not an HTTP-based or web-based solution? And obviously, as I said earlier, it's not always easy to think in Erlang when you're new to it. So that was it. So if you have any questions or any remarks or anything I was wrong about that you guys would like to correct me about. Yeah?
So you mentioned that you're a startup and you switched to Erlang. So how was it finding more people to work with you? Did people know Erlang around you? Did you teach them?
Teaching Erlang is once you have a system in place that has an architecture, it's pretty easy to get people up to speed. That has been my experience so far. We didn't hire that many people on the backend side. We're hiring more on the front-end side because writing JavaScript is much more tedious than writing Erlang. But on the backend side, luckily we managed, when we have been looking around, we managed to get a lot of applications from people who actually knew Erlang. I think it comes from the fact that we are probably the only music startup doing Erlang stuff. I don't know. Yeah?
How did you go about creating your first architecture for the entire application, lacking experience?
It was random. It just worked. But then we just rewrote the whole server back in the summer. There's also there's an entire chapter I didn't talk about, which is the design of the protocol, because that's not really relevant here. But essentially, like, while doing that, we not only had to design the server and the architecture of the server, but also design a protocol that made sense. And we didn't do that in the beginning. We just had random messages.
So how was Erlang at rapid prototyping?
I think it's, for what we were trying to do, it's pretty good. We wrote the whole thing over Easter holidays, and it was working. So, of course, it didn't have all the features that we wanted, but it worked. I mean, I had much more trouble working with node.js than working with Erlang. I don't want to be a troll, or if there is any node.js people who like here, I'm sorry. Yeah?
You mentioned multiple nodes, distributions, scalability problems, and media consistency.
Yeah.
How do you solve this problem?
So, the initial version was really, really simple. So we only have one process, and the process is randomly located on the node, and then clients connecting to one of the nodes will just contact that one, and every single space is a process. Obviously, there is a problem with that, which is like duplicating the message. We don't have a multicast mechanism in Erlang, so you end up duplicating all the messages across the network to send to all these clients that are remotely. So we started, or we have the current version actually is just the same thing, but smarter. So every single space has a repeater or a broadcaster on all the remote nodes. I'm still looking basically for something to work with for this, but the idea that we're thinking of is looking at things like Raft, which is a consensus protocol that just is a new consensus protocol, simpler than Paxos, where actually every single one of the nodes keeps a log of the events that have happened recently. And it also has a state. So it receives the events, put them in the log, and then replay the log on the same state machine. And then while doing that, they also elect a leader, and all the modification operations go through the leader that's going to duplicate the log. So we're thinking about doing that to be able to run the rooms across multiple servers. But so far, we really didn't need to do that because, as I said, the largest event we had was about 6,000 people, 6,500 if I remember correctly, concurrent people in that same room. And it worked pretty well. It sort of like was pretty high up. Like it still was usable. We didn't have any delays. Everything worked pretty well, really. So as long as we don't have these really large rooms, we're able to scale pretty easily across nodes. It's the problem only starts when you have large rooms. Does it answer your question?
Yes, but just to see if I understand the state of the room, the real state is on one server, exactly.
Yes.
Just broadcast to the proxy.
Exactly. So we synchronize the state by replication, by broadcasting modification or transforms basically to all the clients and everyone to actually update their state. Yeah.
It must be really cool to re-implement more or less similar logic or the same application in several different languages within what I understood was quite a short time. Did the choice of technologies or languages affect kind of how the team worked together or the teamwork, or was it just doing the same thing?
The team is, or when we started, we're all founders in that, or most of us founders in Soundrop. And when we started, we were all like polyglots regarding languages. We didn't know the same languages. So one of the guys with us knew Erlang and OCaml pretty well. And so I learned from him. And the other guy was much more like a hardcore C programmer and assembler level stuff. So we're used to, I mean, the team were really used to switching between languages for the things that we need, really. So, and Erlang just worked for the reasons that I explained. So, did that answer your question? Yeah? Yes?
So the way you describe the architecture, I understand that all information is replicated on every server. So all the state is replicated, but there's one leader.
No. That's basically where we would like to go. So right now, the state is only on one single server. And the other nodes are just, so the space process gets booted random, or it's a hash actually, to decide which node to boot on. And then every single time there's a client that connects, that joins that space, and we figure out that they're remote, we spawn a process on the remote node that's going to be a repeater. And then we send the messages to that remote process that's going to replicate. So we sort of like build our own multicast at one single level multicast. The goal is to move to a replicated state. So every now and then, every 10 minutes, randomly between 0 and 10 minutes, the server will actually flush its state to a database. And so when it restarts, it will reload that state. Yes. Sorry. Yeah, it works. It really works for our needs. We don't have that many transactional requests per second. We just like use it as a storage area. We could have used a file system or anything. Really works. None of us really had experience with Ninja from before. That's all. Other questions? No? Okay. Well, thank you very much.